Hayaang buksan ang isipan sa science o agham. Tayo na.
Have you ever been in the middle of your favorite game? Then suddenly, everything shuts down. Your phones will die, and you're left wondering, why does it happen so fast?
Oh no! My phone's about to die! No!
But what if there is a tiny hero inside your devices that helps keep things running, even just for a little while?
Relax, I'm still here.
Whoa! Who are you?
I'm Cap the Capacitor. I've stored some energy.
Wait, you have backup?
Just a little, but enough to keep the system from dying suddenly.
So you hold energy when there's power?
Yes, I store it first, then releases it when needed. Especially during the sudden changes, like this blackout.
Ah, that's why it didn't shut down immediately.
I am the emergency hero of circuits.
Thanks, Cap. That's so cool. I want to know more about how you work.
You guys should meet Professor Wolf. He can explain all the science behind capacitors.
Ah, here they are. Welcome, welcome, young scientists. So you met Cap, our energy story hero.
Yes! Can you explain how Cap actually works?
Of course, imagine this. A glass of water. When you pour water into it, it fills up. And when you get thirsty and drink it, the water is used up. A capacitor works in a similar way. It stores electrical energy, and when needed, it releases it back into the circuit.
But wait, how will it store electricity if it looks empty?
Good question. Inside a capacitor are two plates, like slices of bread, with a special material in between them, like this thread, called an insulator. Even though charges don't touch, something amazing happens. Energy is stored in an electric field between them. If you want, I can show you a demo using Professor Volk's website.
Yes, please!
Before we begin our laboratory presentation, I will first explain the backbone of our program, an interactive simulator designed to demonstrate how capacitors behave in series and parallel circuits. This program is specifically developed to deepen understanding by allowing users to input values, perform calculations, and visualize circuit behavior in real time. Let us start with the overall structure of the system. The program is composed of three main components: the user interface, the computation logic, and the visualization system. These components work together seamlessly to create an interactive and educational experience. First, the user experience is built using HTML and styled with CSS. This is where users can input capacitor values, adjust the voltage, and interact with controls such as add capacitor and calculate. The interface is designed to be clean, intuitive, and responsive, allowing users to easily modify the circuit and observe changes without difficulty. Moving on, the program includes an efficient input and data handling system. At its core is essential object referred to as a state or ST, which stores all capacitor values. Each capacitor added by the user is assigned a unique identifier, and these IDs are maintained in an array for easy tracking. Functions such as add R and remove R enable users to dynamically add or remove capacitors, while the getVals function retrieves and validates all user inputs before any computation is performed. This structure ensures flexibility, allowing the simulator to handle multiple capacitors without a fixed limitation. With the data property managed, we now transition to the core of the program, the computation engine. This is handled by two primary functions, calc series and calc parallel. For parallel circuits, the program directly sums all capacitance values, following the principle that total capacitance is the sum of individual capacitors. After determining the total capacitance, it calculates the charge using the formula. In contrast, for series circuits, the program applies the reciprocal formula. It first sums the inverses of each capacitance value and then takes the inverse of the result to obtain the equivalent capacitance. Once the total capacitance is determined, the charge is computed using the same formula. These calculations are executed instantly whenever the user clicks the calculate button, ensuring real-time feedback. To complement these computations, the program features a visualization system, which is one of the most essential components using an HTML as the program. The two primary drawing functions, draw series and draw parallel, determine the circuit layout. The draw series function arranges capacitors in a single straight path, clearly depicting a series connection, and on the other hand, draw parallel creates multiple branches, placing each capacitor on its own path to represent a parallel configuration. This graphical representation allows user to better understand circuit structures beyond numerical results alone. Now, let us examine the overall program flow. When a user interacts with a simulator, several steps occur in sequence. First, user inputs or modifies capacitor values. Second, the program collects these values through getValues function. Third, it performs the appropriate calculations depending on the selected circuit type. Fourth, the computed results are displayed on the interface. And finally, the circuit diagram is updated and redrawn on the canvas. This entire process repeats dramatically with every user interaction, making the program fully responsive and interactive. Another key feature of the system is its initialization process. Upon launching, the program automatically generates default capacitors and performs initial calculations. This ensures that users are immediately presented with a working example, allowing them to explore the simulator without needing to start from scratch. In conclusion, the backbone of this program relies on three fundamental components. First, a dynamic input system that enables flexible user interaction. Second, accurate computational logic based on established circuit formulas. And third, a real-time visualization system that enhances conceptual understanding. And by integrating these elements, the simulator becomes both a functional tool and an effective educational resource for studying capacitor behavior. And now, for the most awaited part, as I step into our mini lab setup, I see 5 capacitors connected to a 12-volt battery. Each one has a different value: 47 microfarad, 120 microfarad, 330 microfarad, 68 microfarad, and 220 microfarad, making our experiment more realistic and a bit more challenging. A capacitor is like a tiny storage tank for electrical energy, and its ability to store charge is called capacitance, measured in microfarads. Now, here's where things get interesting. Depending on how we connect these capacitors, their behavior completely changes. Let's start with the parallel circuit. Imagine all the capacitors standing side by side, each directly connected to the battery. Parang magkakatabi sila, all sharing the same energy source. And because of this, they all experience the same voltage, which is 12 volts. Since each capacitor stores charge independently, we simply add their capacitance. 47 plus 120 plus 330 plus 68 plus 220 is equals to 785. To find the total charge stored, we use the formula Q is equals to C. Multiplying 785 microfarad by 12 volts gives 9,420 microcoulombs. Ang dami, right? This means that in a parallel setup, the capacitors work together to store more energy. Like a team, where everyone contributes equally to build something bigger and stronger. Now, here's another exciting part. What if we rearrange the same capacitors? Let us smoothly switch from that side-by-side setup into a series circuit, where the capacitors are now connected one after the other. Parang pila sa canteen, passing energy along the line. In this arrangement, the charge is the same across each capacitor, but the voltage is divided among them. Because of that, the total capacitance actually becomes smaller. To compute it, we start with the reciprocal formula. 1 over C total is equals to 1 over 47 plus 1 over 120 plus 1 all over 320 plus 1 all over 68 plus 1 all over 220. When we calculate the right side, we get approximately 0.051. But remember, this is not yet the final answer. Since this is the reciprocal, we still need to take the inverse to find the equivalent capacitance. Therefore, the final answer is 19.6 microfarad. Now, using the same formula for charge, multiplying 19.6 microfarad by 12 volts gives approximately 235.2 microcoulombs. From 9,420 down to 235.2. That's a huge difference. This clearly shows how changing the arrangement alone can drastically affect how much energy the circuit can store. So what did we discover today, young scientists, in our circuit lab? When capacitors are connected in parallel, capacitance increases and more charge stored. But when connected in series, capacitance decreases and the stored charge becomes much smaller. And just like in our experiment, the way things are connected, whether in circuits or even in teamwork, can completely change the outcome. That is the power of understanding how systems like circuits work.
Grabe, I can't believe something so small like capacitors can do that. Right? It may only store a little energy, but it makes a big difference, especially during changes like brownouts.
Of course, I may be small, but I help circuits more stable and prevent instant shutdowns.
Excellent observations. And remember, capacitor is only a part of a bigger circuit system.
Professor, that's where series and parallel circuits come in, right?
Marvelous! Ikaw na! In a series circuit, components are connected in a single path. If one part fails, everything stops. But in a parallel circuit, there are multiple paths for electricity to flow. So even if one path fails, the other can still work.
So that's why some lights stay on even if one bulb breaks.
And that's where I come in too. I help those circuits by storing and releasing energy when needed.
So together, capacitors and circuits help make our devices more reliable.
Precisely. Thanks to our Professor Vault website, you can explore these concepts interactively. See how capacitors charge and discharge, and how series and parallel circuits behave in real time.
That's so cool. Learning science feels like playing a game. Yeah, no more boring lectures. This is way more fun.
Told you, science has power.
So remember, young scientists, even a smallest component can have a big impact. So all together, stay curious, stay powered,
And keep on learning.